Okay, so now Wilson's theorem says that let P be a prime number with P bigger than 2. Or we don't need actually P bigger than 2, just any prime number. Let P be a prime number, then P minus 1 factorial is congruent minus 1 mod P. P minus 1 factorial congruent minus 1 mod P. So recall the definition of factorial. I'm sure you know about it, right? So n factorial means 1 times 2 times 3 all the way to n. And 0 factorial is defined to be 1. We don't need 0 factorial here because P is at least 2 and P minus 1 is at least 1. But just to remind you about factorials. So n factorial means you multiply 1 with 2 all the way to n. So 3 factorial, for example, is 1 times 2 times 3, which is 6. 4 factorial, 1 times 2 times 3 times 4, which is 24, and so on. So for example, if P is, for example, 5, 5 minus 1 factorial is 4 factorial equals 24, which is congruent minus 1 mod 5, right? Because 5 divides the difference between 24 and minus 1, because 24 minus 1 is 25, which is divisible by 5. So always we can say that P minus 1 factorial is congruent minus 1 mod P. And this is an example. Now let's see how we can prove. And of course, you know that this is just an example, not the proof for Wilson's theorem. Proof has to be in general. This is just an example of Wilson's theorem, but proof has to be in general. So it must be valid for every prime number P. So proof of Wilson's theorem. So P minus 1 factorial means what? Means 1 times 2 times 3 all the way to P minus 2 times P minus 1. So mod P, now mod P here is the list of numbers that we need to multiply So remember, we are trying to prove a congruence mod P. So that means every calculation that we are doing is mod P. Or in other words, our universe, like I said before, and the break in the first video, our universe is ZP here. And every calculation is mod P. Now, which numbers do I need to multiply? So look at the list of numbers that I have to multiply. 1 and then 2, 3, all the way to P minus 2 and also P minus 1. So 1 is one of them. Now P minus 1. So the first number is 1. But now let's look at also the last number. Last number is P. The first number is 1. The last number is P minus 1. And P minus 1 mod P, remember every calculation is mod P. P minus 1 mod P is minus 1. What about the other numbers 2, 3, 4 to P minus 2? So in total, I have P minus 1 numbers. So apart the first two numbers, how many is left? So this is P minus 3 numbers. Okay, so I want to say here that each of these P minus 3 numbers is going to be paired with another element in this list, and multiplication of them will give me 1. So the claim here is, let me call this one, for example, A, P minus 2, which is a set with P minus 3 elements, right? Each of elements of A, or each element of A, say for each element of A, for each element A in A, there exists an element B in A with B not equal to A, such that AB is equal to 1. So every element in A is going to be paired up with another element in A that their product is 1. So once this this claim is proved, we have our Wilson's theorem. Why? So once the claim is proved, what can we say once the claim is proved? And we can write the product of elements of A as, so 2 times 3 elements of A were, 2 to P minus 2. So 2 times 3 to P minus 2. I can write it as 2 times 2 inverse. Inverse, by inverse, I mean inverse mod P, right? Such that AB equals 1, of course, in ZP, I mean. i.e. B equals A inverse in ZP. So inverse, I mean inverse in ZP means the number that when you multiply with the original number, you get 1 in ZP. So 2, so this claim says that every element here in A is going to be paired up with another element in A that they are inverse of each other. So when I multiply all the numbers in A, 2 to P minus 2, so 2, according to the claim, has 1 inverse in A. I don't know which number, I just know one of the numbers in A is inverse of 2. So 2 is paired up with inverse of 2. And then 3 with inverse of 3, and so on. So in total, I will have, so this is, let's say, 1 pair. If I consider this as 1 pair, so 2 numbers, but 1 pair, each number is paired up with its inverse. So in total, I would have P minus 3 over 2 pairs, each with product 1. 2 and 2 inverse, then 3 and 3 inverse. And in total, A has P minus 3 elements. So P minus 3 over 2 pairs, that the product of each pair is 1, because for each pair I'm multiplying a number with its inverse. So in total, when I multiply all the elements of A, I get product of P minus 3 over 2 ones. And product of any number of ones is, of course, 1. So this is 1 times 1. P minus 3 over 2 times, which is 1. Again, of course, in everything, as I said, in ZP, means everything is, all the calculations are done mod P. Okay. And once we know that the product of A is 1, so what is P minus 1 factorial? Then we will have P minus 1 factorial equals 1 times minus 1 times product of elements of A Or let me write just 2 to p minus 2, which is same as product of elements of A. And this one is 1. We just showed that this one is 1. So the answer is going to be 1 times minus 1, which is minus 1 in ZP. So it remains to prove the claim. Okay. Now consider, so let me say given, let's say some element A in A, consider AX congruent 1 mod P, which means, AX equals 1 in ZP. Since GCD of A and P equals 1, P is prime and A is some number between 2 to P minus 2. So every element, when you have a prime number, every element is relatively prime, except the prime number itself and or the multiples of P. So GCD of a prime number and any number in the world is 1, unless that number is the prime number itself or a multiple of that prime number. So A here is not a multiple of P because it's either 2 or 3 or P minus 1, 2. So GCD of A and P is 1. Thus, AX equals 1 or congruent 1 in P has a solution by a theorem we saw before. See, do you remember we had a criteria? We derived a criteria that determined where AX equals 1 mod M has solution and when it does not have solution. If GCD of A and P, in that case we said M previously, but here our M is P. If GCD of A and P is 1, then this one has a solution. So it has a solution in ZP, say X equals B. So AB equals 1 in ZP. Now note, so there are a few things that still has to be proved. First of all, we said that the inverse, so B is inverse of A because AB is 1. But inverse, we said that the inverse has to be in the set A itself. And what was the set A? A consists of almost all the elements except 1 and minus 1. But if A is in set A, B has to be in A as well, meaning that B cannot be 1 or minus 1. Why? So note that B has to be in A, since B is not equal to 1 and B is not equal to minus 1. As B equals 1 is the inverse of A equals 1 and B equals minus 1 is the inverse of A equals minus 1, which is not in A. See, one number cannot be inverse of two numbers, two different numbers. Now, 1 is inverse of 1, and minus 1 is inverse of minus 1. And 1 and minus 1 are not in A, right? So if 1 is inverse of 1, it cannot be inverse of a number in A anymore. Remember, A is in A, right? Okay, A is in A. Now, inverse of A cannot be 1. Why? Because 1 is inverse of 1 itself, and 1 is not in 1, and 1 is not in A. So 1 cannot be inverse of A. which is in A. Similarly, -1 is inverse of -1, and -1 is not in A. So because A is already used for a letter that was in A, so let me call this one, for example, T. One is inverse of T equals 1. So it cannot be inverse of A. Remember, each number is only allowed to be inverse of one number. It cannot be inverse of two different numbers. So if one is inverse of T equals 1, it cannot be inverse of A anymore. And similarly, if -1 is inverse of T equals -1, it cannot be inverse of A anymore. So B is in A because it's not 1 and it's not -1. So that means B is in A. Also note that B is not equal to A. So let's look at the claim. I'm proving the claim right now. The claim says for each element A in A, there exists an element B in A, that B is not equal to A and B is inverse of A. So there are few things that are mentioned in the claim that have to be proved. First of all, it says that any element A has an inverse B. So this one we proved that every element A in A has an inverse B. Now that inverse, which we are calling it B, has to be in A. That one also, that is also proved. Also, that inverse has to be not equal to A. So why we are now proving is not equal to A? Why B is not equal to A? Because otherwise B will be equal to A, right? So AB, we know that AB is equal to 1 in ZP. And if B is equal to A, that means A squared equals 1 in ZP. Okay, it seems that the screen is freezed. Let's stop share. Share again. But A squared equals 1 in ZP has only two solutions. We saw in example above that A squared equals 1 in ZP has only two solutions, which is A equals 1 and A equals -1. Do you remember? I gave two solutions for this for you. Here, x squared equals 1 in ZP has only two solutions, x equals 1 and x equals -1. And we provided two solutions for this. So, but neither of these numbers are in A. So that means B is not equal to A. Remember, original A was supposed to be in A, capital A. But here I got this basically proof by contradiction. If B is equal to A, then A has to be either 1 or -1, but neither of these numbers are in A, which means B has to be not equal to A. That's it. So that means claim is proved. Okay, let me explain one more time about the proof of Wilson's theorem. I think got a little bit long and maybe I've lost the track. So let me explain one more time the idea. So first of all, what does Wilson theorem say? It says that if p is prime number, p minus 1 factorial is equal to minus 1 mod p. Now, how do we prove this? So let me explain the idea. P minus 1 factorial means what? Means 1 times 2 times 3 all the way times p minus 2 times p minus 1. Now I want to rearrange this product. So this product is same as 1 times minus 1. So look at the first number. First number is 1. I wrote 1. Look at the last number. Last number is p minus 1. P minus 1 is same as minus 1 mod p. So the last number is minus 1. And then I wrote the rest of numbers, 2, 3, 4, all the way to p minus 2. How many numbers are there here? P minus 3 numbers. P minus 3 numbers, because total numbers p minus 1. 2 of them I separated. So p minus 3 numbers are left. Now, this number times this number is, of course, minus 1. Now, if I show that the product of these numbers are 1, then that means the whole p minus 1 factorial will be minus 1. So it's only left to show that product of these numbers are minus 1. Now, how do I do this? Well, I say that my claim is every element that I call the set of these elements capital A. So I said every element in capital A that you consider, it has an inverse inside this capital A that is different than the number itself. So for example, 2 has an inverse among these elements. And inverse of 2 is not 2 itself. It could be anything else. I don't know which one. Well, that depends on P. Remember the proof, we are doing the proof in general. So you can do some examples if you want to get the idea. Let's say, for example, if P is 11, what is inverse of 2? What is inverse of 3? So inverse of 2 and inverse of 3 depends on P. It could be maybe P minus 2, maybe P minus 5, depending on the value of P. But because I want to give an argument that works in general, I cannot say that inverse of 2 is which of these numbers. I can only say that inverse of 2 is one of these numbers. Which of these numbers, that I don't know. That depends on P. So inverse of 2 is one of these numbers, either 3 or 4 or all the way to P minus 2. I called it 2 inverse. Similarly, if I prove the claim, that means 3 also has an inverse among these numbers, which is not 3 itself. And I called it 3 inverse, and so on. So when I multiply these numbers, each of these numbers is paired up with one of the elements, one other element in this set A. And therefore, I will have P minus 3 over 2 pairs. Product of each pairs is 1. I'll get a bunch of 1s multiplied together, and the answer is 1. And that will be it. So the only thing that is left to show is to prove the claim that every element in A has an inverse in A. And that inverse, which I'm calling it B, is not same as A. And is in A itself, in the set A itself. So first of all, I am saying that, okay, let's assume that we have some element A in A. First of all, this element must have an inverse. Why? Which numbers have inverse in ZP? If a number is multiplied with another number and the result is 1, then that means the number has inverse. So if AX equals 1 has a solution, in other words, then A has an inverse. Well, AX equals 1 has a solution. Why? Because GCD of A and P is 1. And we have had a theorem before that said under these circumstances, A has an inverse. So A has an inverse. I am calling the inverse B. So the inverse, I called it B, so AB equals 1. So, but I'm not done yet to prove the claim. To prove the claim, I have to show that this element B, which is inverse of A, is also in the set capital A. And also, the element B has to be not equal to A. So to show that is in capital B is in capital A, What was capital A? Capital A is the set of elements 2 to p minus 2. So basically every element is ZP except 0, 1, and minus 1. So of course, B cannot be 0 because 0 has no inverse and is not the inverse of any number either. But this element B cannot be 1 and minus 1 either. Why? Because 1 is inverse of 1 itself. So, and 1 is not in A. So that means if B equals 1 is the inverse of T equals 1, then that means B equals 1 cannot be inverse of small a anymore, right? Because one number cannot be inverse of two numbers at the same time. Similarly, if B equals minus 1 is the inverse of T equals minus 1, it cannot be inverse of small a anymore. So B is not equal to 1, not equal to minus 1, therefore it has to be in A. And lastly, we have to show B not equal to A. This is proof by contradiction. If B is equal to A and AB is 1, so that means A squared is 1. But before the break, in the first part 1 of the lecture, we showed that A squared equals 1 has only two solutions, 1 and minus 1. Neither of these numbers in capital A, but small a was in capital A. So that's a contradiction, which means B has to be not equal to A. Okay, now we are ready to show or to prove Fermat's Liddell theorem. So let A in ZP with A not equal to 0. We want to show A to power P minus 1 equals 1 in ZP. So consider these elements. So A, 2A, 3A, all the way to P minus 1 times A. So again, the claim is any two of these elements are distinct. They're different. Any two of them that I consider different. Why? So since if IA equals JA for some I not equal to J with I and J both between 1 and P minus 1, of course, again in ZP, every equality is in ZP. Then what can I say? Then I can say that IA congruent JA mod P, that means P divide IA minus JA, which means P divide A times I minus J. So that means P divides A or P divides I minus J. But P divides A is not possible since A is not equal to 0 in ZP. P divides A means A equals 0 in ZP because P divides A means A is a multiple of P, and the multiple of P is equal to 0 in ZP because the multiple of P is divisible by P and therefore is congruent to 0 mod P. And P divides I minus J is also not possible. Why? Because I and J are both between 1 and P minus 1 and I not equal to J. So I minus J will be, let's say in absolute value, is bigger than or equal to 1. and less than equal to p minus 2. So if you subtract two numbers, both between 1 and p minus 1, and they are not equal to each other, so there you get a number which is at least 1 and at most p minus 2. And none of the numbers between 1 to p minus 2 are divisible by p. P is prime, so and none of the numbers in 1 to p minus 2 is divisible by p. Now, of course, even if p is not prime, still we can say that none of the numbers in 1 to p minus 2 is divisible by p, but here p is also prime. Okay, so I proved my claim that any two of these numbers are distinct. So what does that mean? Thus, the claim is proved. So we have p minus 1 distinct elements a to p minus 1 times a, and none of these numbers are 0, right? Because a is not 0. Remember, my original assumption was that a is not 0. So if a is not 0, 2a is also not 0, all the way to p minus 1 times a is not 0. Remember, we are in ZP. Our universe is ZP. So 0, of course, is 0. And also any multiple of p is 0. But because we are multiplying either 1 or 2 all the way to p minus 1 times a, so none of these numbers are 0, 1 or 2 or p minus 1. So none of these numbers are 0. And none of these numbers are 0. So what does that mean? So thus, this set as a set, let me say a to p minus 1 times a. So I have p minus 1 distinct elements in ZP. But what is ZP? ZP is 0, 1 to p minus 1. See, let's say ZP is 0, 1 to p minus 1. So ZP has p elements. One of them is 0 and p minus 1 non-zero elements. Right now I have p minus 1 distinct non-zero elements. So these elements must be 1 to p minus 1, of course, in a possibly different order, but the order is not important for me. So the only thing that is important for me is that this list, the list of these numbers is same as the list 1, the list of the numbers 1, 2, all the way to p minus 1. Why? Because here I have p minus 1 distinct elements in ZP, which means almost I have all the elements in ZP except 0, because if I put the 0 aside, and I have to put 0 aside because none of these numbers are 0, I have p minus 1 elements left in ZP, and these are p minus 1 distinct elements in ZP. So that means these numbers must be same as these numbers. As I said, possibly in a different order, but the list of these numbers must be same as list of these numbers. Okay. So what does that mean? Thus, a times 2a times 3a times p minus 1 times a is equal to 1 times 2 times 2p minus 1, right? So the list of these numbers is same as list of these numbers. So the product or multiplication of these numbers is same as multiplication of these numbers. You have two lists of numbers. So let's say list 1 and least 2. They are the same numbers, possibly in a different order. For example, let's say 2, 4, 8 here, and then 4, 8, 2 here. Possibly in different order, but they're same numbers. So if I multiply these numbers together, compared to multiply these numbers together, of course I get the same answer, because when you multiply, the order is not important. Now, p minus 1 factorial is what? So because the right-hand side, 1 times 2 times p minus 1 is p minus 1 factorial, which is equal to -1 by Wilson's theorem. Again, it's ZP. And what about the left-hand side? What can I say about the left-hand side? So left-hand side, I have product of p minus 1 a's, so a to power p minus 1, and then 1 times 2 times 3 all the way to p minus 1. That's p minus 1 factorial. So times p minus 1 factorial. So I can say that a to power p minus 1 times p minus 1 factorial equals -1 in ZP. Right side was -1, right? And again, p minus 1 factorial is -1. So I can say minus a to power p minus 1 equals -1 in ZP. And I can multiply both sides with -1. I'll get a to power p minus 1 equals 1 in ZP, which is what I needed. And lastly, to show a to power p equals a, again in ZP, for every a in ZP, because remember Fermat's little theorem had two parts. First part said a to power p minus 1 equals 1 if a is anything except 0 in ZP, which means every integer except multiples of p. And the second part said a to power p equals a for every number, whether multiple of p or not multiple of p. In other words, in ZP, whether it's 0 or not in ZP. Well, this is now very easy to prove. So case 1, if a is not equal to 0, then we know that a to power p minus 1 equals a equals 1. That's what the first part said, a to power p minus 1 equals 1. And if I multiply both sides by a, I get a to power p equals a. And case 2, if a is equal to 0, well then 0 to power p equals 0. That's obvious, right? So in any case, a to power p equals a for every a in ZP. Okay, so we did the proof, we did an example, we did some theorems to prove Fermat's theorem. We proved Wilson's theorem. We could prove the Fermat's theorem even without Wilson's theorem, but because Wilson's theorem is also important on its own, and it was also in the book exercises, I wanted to state and prove it, that p minus 1 factorial equals -1 mod p, and Fermat's theorem says a to power p minus 1 equals 1 mod p if a is not equal to 0. Okay, another topic related to this is a concept called primitive root or primitive root of unity. Primitive roots of unity in ZP. So definition, R in ZP is called a primitive root of unity if p minus 1 is the smallest power, such that r to power p minus 1 equals 1 in ZP. So we know that r to power p minus 1, if r is not 0, of course, we know that r to power p minus 1 equals 1 according to Fermat's-Leda theorem. But if p minus 1 is the smallest power that r to that power equals 1 in ZP, then we say r is a primitive root of unity. Now, primitive root of unity, unity means 1. Root of unity means a number that one of its powers is 1, right? For example, root of 4 is 2. Why? Because 2 to power 2 is 4. Now, root of unity means the power of r is 1. And primitive roots of unity means, the power p minus 1 here is the smallest power that such that r to that power gives 1. So why is this concept important, primitive root of unity? Why is it important to have a number that r such that p minus 1 is the smallest power that r to power p minus 1 can give 1? So the important feature is, if we say important feature, so if r in ZP is a primitive root of unity, then every element of ZP except 0 is a power of r. Why is this proof? So consider the numbers r, r squared, r cubed, all the way to r to power p minus 1. So this is a set of, so claim this is set of p minus 1 distinct elements in ZP. Why are they distinct elements? If not, what do we have? What would we have? We would have, let's say, Ri equals r to power a equals r to power I equals r to power j for some I and j between 1 and p minus 1. Say with j bigger than I. So two of these powers, if they are not all distinct, two of them would be called, let's say, r to power I with r to power j. And then one of the powers would be bigger. I called the bigger power j and the smaller power I. So, and everything again is in ZP. So if r to power I equals r to power j, then what can I say? Then I can say p divides r to power I minus r to power j, the difference between powers of r. And what does that mean? So I is the smaller power, so that means p divides r to power I times 1 minus r to power j minus I. But remember, r is a primitive root of unity. assumption, see if R is primitive root of unity. Primitive root of unity cannot be 0. Why cannot be 0? Because I want p minus 1 to be the smallest power, that R to power p minus 1 is equal to 1. But 0 to any power is 0, it's not 1, right? So any primitive root of unity cannot be 0, because 0 to any power gives you 0. It will never give you 1. So if R is not 0, that means R is not divisible by P. So see, this means P divides R to power I, or P divides 1 minus R to power J minus I. But this is not possible because R is primitive root of unity, and hence R not equal to 0 in ZP. If R is not 0 in ZP, that means R is not a multiple of P. Therefore, powers of R are not multiples of P either. P is a prime number. If in the prime factorization of R, there is no factor P, in the powers of R still in their prime factorization, there is no factor of P. So that means this would be true. Thus, we will have P divides 1 minus R to power J minus I, which means 1 minus R to power J minus I equals 0. In ZP, remember again, in ZP, any multiple of P is 0. And that means R to power J minus I equals 1. ZP, and J minus I is less than P minus 1, right? See, what are I and J? I and J are two numbers between 1 and P minus 1. If I subtract two numbers between 1 and P minus 1, of course, the result will be strictly less than P minus 1. And this is contradiction with R being a primitive root of unity. Primitive root of unity means P minus 1 is the smallest power that R to that power gives you 1. But right now I found R to power J minus I equals 1, and J minus I is a smaller power compared to P minus 1. So I proved the feature, important feature of primitive root of unity, that the power, any number in ZP except 0 can be written as a power of R, if R is a primitive root of unity. So let's look at an example. Is R equals 5 a primitive root of unity in Z11? Or is it R equals 3? So let's look at the powers of 3. If P minus 1, which in this case P is 11, if 10 is the smallest power, that 3 to power 10 is 1, then 3 is a primitive root of unity. Otherwise, it's not. So let's look at powers of 3. Powers of 3. So 3 to power 1 is 3 in Z11. 3 to power 2 is 9 again in Z11. 3 to power 3 is 27, which is same as 5 in Z11, right? Because 27 minus 5 is 22, which is divisible by 11. So 27 is same as 5 in Z11. 3 to the power 4. What about 3 to the power 4? So that's going to be 5 times 3, because 3 to the power 3 is same as 5. So 3 to the power 4 is same as 5 times 3, which is 15. And 15 is same as 4. Z11. 3 to the power 5. 3 to the power 4 is 4. So 4 times 3, which is 12. 12 is same as 1 in Z11. So 3 to the power 5 is 1. So that means 3 is not a primitive root of unity in Z11. Because if it was, then 10 had to be the smallest power. That 3 to that power gives you 1. The 5 is less than p minus 1, which is 10. Okay, so for now, another example is r equals 2, a primitive root of unity in Z11. For r equals 2, what are the powers of 2? So let's check powers of 2. So 2 to the power 1 is 2, which is, same as 2 in Z11. 2 to the power 2 is 4 in Z11. 2 to the power 3 is 8 in Z11. 2 to the power 4 is 16, which is same as 5 in Z11. 2 to the power 5 is 5 times 2, because 2 to the power 4 is 2, and 2 to the power 4 is 5. So 2 to the power 5 means 5 times 2, because 2 to the power 5 is 2 to the power 4 times 2, but 2 to the power 4 is 5, so it's 5 times 2, which is 10 in Z11. 2 to the power 6 is 2 to the power 5 times 2. 2 to the power 5 is same as 10. So 10 times 2 is same as 20. And 20 is same as 9 in Z11. 2 to the power 7 is 2 to the power 6 times 2. So that's 9 times 2, which is 18. And 18 is same as 7 in Z11. 2 to the power 8 is 2 to the power 7 times 2. 2 to the power 7 is 7. So 7 times 2, 14, which is same as 3 in Z11. 2 to the power 9 is the previous one times 2, so 3 times 2, that's 6 in Z11. 2 to the power 10 is the previous one, which is 6 times 2, which is 12, and 12 is 1 in Z11. So that means 2 is a primitive root of unity in Z11. Two is a primitive since the smallest power of 2, which gives 1, is p minus 1 equals 10. Also note, as predicted by important feature above, do you remember what we proved as important feature. Important feature proved that if R is a primitive root of unity, then every number in ZP except 0 can be written as a power of R. So as predicted by important feature, power every element in Z11 except 0, which is same as 1, 2, all the way to 10, can be written as a power of R equals 2. Look at the power, 2 is a primitive root of unity here because 2 to power 10, 10 is the smallest power that 2 to that power gives us 1. But look at the powers of 2 here. The first element is 2, then is 4, 8, 5, 10, 9, 7, 3, 6, and 1. So see, I have all the elements from 1 to 10 when I look at the powers of 10. Of course, they're not in order, and we did not claim that it's in order. We just said that all the powers of all the elements in ZP except 0 can be written as a power of 2. And here you are. So 1, the first element, can be written as 2 to power 10. Then 2, where is 2? 2 is 2 to power 1. 3, where is 3? 3 is 2 to power 8. Then we have 4. 4 is 2 to power 2. 5 is 2 to power 4. 6 is 2 to power 9. 7 is 2 to power 7. 8 is 2 to power 3. 9 is 2 to power 6. And 10 is 2 to power 5. So all elements in Z11. Z11 means what? Means 0, 1, all the way to 10. So every element in Z11 except 0, which means 1 to 10, can be written as power of 2. So this is an example of the important feature which we proved it in general. Okay, guys, so this is about primitive roots of unities. So Fermat's theorem guarantees for us that a to the power p minus 1 is always equal to 1. So r to the power p minus 1 is always equal to 1 in ZP if r is in ZP a non-zero number. But if that p minus 1, if that number p minus 1 is the smallest power that r to that power is 1, then we call r primitive root of unity. So 2 was primitive root of unity. But in the previous example, 3 was not primitive root of unity because 3 to the power 5 was 1. Of course, 3 to the power p minus 1, which means 3 to the power 10 is still 1. But 3 to the power 5 is also 1. So p minus 1, which is 10, is not the smallest power that gives us 1 in the case of r equals 3, because 3 to the power 5 is also 1. And in that case, r equals 3 was not a primitive root of unity. Okay, guys, so next time on Thursday, we will have test number 2 from 8:30 to 10:30 p.m. Vancouver time. And we'll continue the lectures and the topics next week. Okay, so see you on Thursday.